So in the next set of foils, I'd like to talk about some manufacturing issues and pitfalls that you have to watch out for while doing your designs. One of the first issues that is manufacturing issue, it's not related to design rules, but it's due to just the way process steps work, is antenna rules. So what winds up happening is as you're creating your metal wires, typically etching away your metal, so you'll put down like metal everywhere and then you pattern it and you might etch metal away in certain spots. But metal wires are plasma etched, so generally in order to get the nice sharp edges on your metal wires, you use a plasma rather than liquid etches, and that plasma, because it's a charged plasma, creates a large voltage charge on your metal wires. Now, if those metal wires are connected through various different layers of metal down to your transistor gates, and they get a large voltage charge on them, a large voltage across your gate oxide will destroy your thin gate oxides. So basically this is called a plasma-induced gate oxide damage, or the antenna effect. So if you damage your gate oxides, this can eventually lead to an increase in your gate leakage currents. It can change your threshold voltage of your transistors, can reduce the life expectancy of the transistor. So you might find that when you're first running the IC chip, it works fine, but after 2, 3, 4 years, a transistor might stop working, or it could just completely destroy the transistor right from the outset. During your high temperature plasma etch stage, when you're doing your plasma etch, you can get a high temperature develop in addition to high voltages. Since your temperature is higher, your PN junctions actually can have a fairly significant reverse bias current or forward bias current, depending on how the charge builds up during the plasma etches. So it turns out if you have PN junctions attached to your metal lines, they'll actually bleed off the voltage charge as it tries to charge up. So PN junctions are fine to connect to metal wires, but you don't just want gates connected to metal wires. And it turns out if you have a PN junction and a gate both connected to a given metal wire, the PN junction will bleed off that voltage. The amount of current that can flow in the PN junction will bleed off the voltage before it damages the gate. So there's specific antenna rules that specify if you have a metal area that's connected to just a gate, there's only a maximum amount of metal that can be connected to a given gate area, otherwise the gate could be damaged. But if you have a larger amount of metal, let's say that would normally damage the gate, if the metal is also connected to a diffusion, then that will actually be legal, because the diffusion will bleed off the voltage that would normally build up there. So let's go through this in a little bit more detail. So the figure here below, you can see, shows a potential problem where we have a driver on the left-hand side. So let's look at situation A, where we have a driver, a drain connected to a metal 1 wire, and it's trying to drive all the way to the gate that's on the right-hand side. Now, if we just had a metal 1 wire connected directly from the diffusion to the gate, we would probably be okay, but it turns out for whatever reason you had to go from metal 1 up to metal 2 and then back down to metal 1 toward the driver side. And so we have a long metal 1 wire that's connected to the gate, and you might say, well, it's connected through metal 2, but the thing is, while we are doing the processing step for the metal 1 patterning, metal 2 doesn't exist yet. So we only have the metal 1 there. So we have two distinct connections of metal 1. There's a short metal 1 connected to our diffusion on the left, and there's a long metal 1 connected to the gate on the right. So basically, we're not going to be connected to the metal 2 until later, and while we're etching the metal 1 for the metal 1 stage, the gate on the right could be damaged. So one of the ways that we can fix this, fix number 1, is shown in part B there of the figure, where we can add another metal 2 jumper near the gate side. So if we're processing just metal 1, you'll see we now have 3 different segments of metal 1. We have a short segment on the left, a short segment on the right, and a long segment in the middle. The long segment in the middle might get charged up, but it's connected to nothing. And so while we're processing metal 1, even if it gets a lot of charge buildup on it, it's not going to damage any gates because it's not connected to any gates. And the short segment of metal 1 on the right is likely short enough, according to the antenna rules. You have to make sure that it passes, but as long as it's short enough that that short segment won't build up enough charge to damage the gate on the right. So that's one potential fix. Fix number 2, as shown in part C of the figure below, is we can add an additional diffusion. It won't be driving anything, it could just be a reverse bias diode that's added near the gate on the metal wire on the right hand side. So we might have that long metal wire, but we can add this additional diode diffusion that will wind up causing any charge that builds up to be bled off as you're processing the metal 1 wire. So that, as long as the diode is large enough, you just need a certain size depending on the length of metal. That would be another way to fix it. Then finally, a third fix that's not shown here, if you can find a way to get rid of the metal 2 jumper that's near the diffusion on the left hand side, then the diffusion that you have on the left hand side might be enough to bleed off, depending on how much metal you have and how long the metal wire is, etc. That might or might not fix your problem, but it's a possible way to fix the problem. Usually it does. If you don't have jumpers on a metal and you just have a driver and receiver on the same layer of metal, normally that's enough to fix any antenna rule issues that you might have. Some additional manufacturing issues that we run into in modern microprocessor or CMOS design is layer density rules. These are also called fill rules. So in effect, each layer that you pattern, whether it's like a poly layer or any of the metal layers, via layers, every layer has minimum and maximum density requirements. So you can't have 90% of that layer is consumed with, like, let's say metal 1. You can't have all really wide metal layer, metal tracks, and every single metal track filled with very small spaces, and then a really wide, very small space, really wide wire, very small space. So there's a certain maximum density you can have, and you also can't have less than a certain minimum. You can't have like a metal wire and then a 20x space to the next metal wire that's minimum and another 20x space and have very little metal. The reason for this is because when you're doing, like I said, between layers, you try to planarize your wafer. So you do this chemical mechanical polish. Well, it turns out if you have too much metal density or too little metal density, the chemical mechanical polish will actually etch too much or too little, because it'll etch more or less in areas that have a difference in the amount, the percentage of metal. If there's a higher percentage or a lower percentage, it'll etch at a slightly different rate. And so you don't want to have large variation in your wire thicknesses due to the fact that your etch is going to happen at a different rate depending on metal density. So they have rules on how much metal you have. If you don't have enough metal, there's checks that will go in and add additional metal. And if you have too many metal lines, you have to actually go in and remove some. So there's various different checks that will check to make sure your density is greater than a certain minimum and less than a certain maximum. For example, you might have your metal density is required to be between 35 and 65%, just as an example. And so there's checkers that go through and they look at any given, they'll look at a window worth of like maybe a 50 by 50 micron area of your chip, and they'll step across your die, make sure that any 50 by 50 micron area has a density that's within the range that they're checking for. If you violate the density, like I said, you'll either need to go in and manually remove some tracks, or if you have too little, there's automated tools that will go in and just fill in with dummy metal that is floating. It's, in a lot of cases not hooked up to anything. Sometimes the dummy metal is floating. Sometimes they'll auto connect it to either a VCC or a ground wire, just depending on how you set your fill flow. Another additional manufacturing issue are what are called resolution enhancement rules. These are things that are required you to do in the layout in order to put restrictions on some of your layers and some of your feature sizes based on the fact that you're trying to build features that are smaller than the wavelength of light that you're using in your optics. So some of these resolution enhancement rules might be things like I've said before. You might require all of your poly to be single direction. So if you don't have corners, it makes it a lot easier to make all of your poly the exact same width, or you don't need to do as much optical proximity correction if all your poly is in a single direction. Or you might have single direction M0. For a lot of the processing generations, your metal 0 might be something that could go in multiple directions, either up, down, or left, right, or have corners and jog around. But with some of the more recent process technologies of the last couple of years, you might have a single direction metal 0. You're not allowed to have jogs in it anymore. Other rules might be things like exact width and space of poly. So, for example, when you're doing FinFETs, they, for the most part, create exact identical array of FinFETs everywhere, which means not just the width of, or the height of the fin, which determines the width of the device, but the device length. So the poly width defines what the device length is, and that's often required to be the exact same everywhere as well. So you just have this array of FinFETs across the entire die that are all the exact same, identical width, identical height, identical length, and you just connect up however many you need for your particular application. You hook up more in series or more in parallel to get slightly different behavior. Some other rules might be your metal width and space. Instead of allowing your metal width to be any value, once you get above minimum, So let's say if your minimum width metal was, you know, 30 nanometers, instead of allowing you to have a 30 nanometer or a 32 nanometer or 33 nanometer width, they might say, no, you're only allowed to have an integer multiple of the minimum width. So if it's 30 nanometers minimum, you're allowed to have 30 nanometers or 60 nanometers or 90 nanometers or something like that. And then, you know, those are some of the easier things that I can talk about. There's many other complex combinations of width and space checks that you can run into. Again, this comes back to you're trying to create feature sizes that are smaller than the wavelength of light, and so there's certain combinations of widths and spaces where the light might either add up or subtract in such a way that you can make it work with just the right, you know, a 2x width with a 1.5x space might work perfectly fine, but a 2x width with a 2x space might not work at all, just depending on your light wavelength and the patterns that you're trying to make. So, so just to keep in mind, in the most modern manufacturing processes, the combinations and the checks that are being done can get very complex. So another manufacturing issue is things that can be done to enhance yield. So if you can add, like for example, extra wire space, so spacing between your wires, if you can make it a little bit more than minimum, you can reduce your capacitance, but you also can get fewer shorts. If you use non-minimum wire widths, so if you use minimum wire widths everywhere, obviously you can get better density and more wire tracks. But if you can use non-minimum wire widths, you not only reduce your resistance, but you'll get fewer opens. So when you use minimum wire widths on your lowest metal layers, you might accidentally get opens every once in a while or other problems. And one other thing that can sometimes enhance your yield is if you're doing an array of transistors, making sure you put dummy transistors at the edge of your arrays. It will help improve your uniformity, because making sure that something next to your transistor looks exactly the same as something next to every other transistor in the array helps that transistor look the same. If you have things next to a transistor that you care about that are different than things next to a different transistor that you care about, those two transistors might behave slightly different than each other. So at the edges of your arrays, if you make sure that you have dummy transistors to make everything look identical as the transistors that are at the center of the arrays. And one final thing I'll talk about with manufacturing issues is something called metal slotting rules. So as I mentioned earlier, some process technologies might say you're not allowed to have metals over a certain width because it might cause problems with density and other things. Other manufacturing processes might say, okay, we'll allow wider metal wires, but if you get to too wide, because of these density issues, we're going to require that metal wire to have basically slots in it, gaps. It's not allowed to be continuous all the way across. So slots are basically long slits of gaps in the metal running parallel to the current flow. They allow the metal to be a lower density. They'll provide some additional stress relief if the metal, with temperature cycling and other things, they'll actually aid in adhesion to the wafer surface. So you might think, oh, it's better to have a solid piece of metal in order to adhere to the surface. Turns out it's actually a little bit better to have some slots there in order to adhere to your surface. And it will also reduce what's called electromigration failure. That's where if you have a large current going through a wire, the metal will actually sometimes flow a little bit, and in flowing, that metal can eventually cause opens or other problems or shorts to neighboring wires. And so this will reduce that. So the figure on the right kind of shows an example of a wide metal power bus with some slots in it.